Okay, now we're going to continue section 712, where systems comprising of several loads. And what we're going to do is we're going to actually make these calculations in terms of the determinations that we need for the particular loads that are connected to this complicated circuit. So all we have to do is once we've identified the type of load, and I tried to go through this and sort of color code this for us. I didn't actually finish that. I need to do that there, and that there, and this here, and this here, and that there. Now, once I've done that, all I have to do is go through here and I find all the active power that would be power going away from the source, and I just add them together. I've got one here, and I've got one here, and I got one here. So the active power P is equal to 2 plus 8 kilowatts plus 14 kilowatts for a total of positive 24 kilowatts. Next thing I'm going to do is I'm going to look at the reactive power that's absorbed by the system. Okay, the active power that's absorbed by the system. And here I'm looking into my greens. So absorbed, AB, is equal to 5 plus 7 plus 8, which is positive 20 kVAR, because these are inductive. The net reactive, the power supplied by the capacitors, the ones pointing in the opposite direction, would be, I'll take that as supplied, that would be -9, since we're saying it's going in the opposite direction, plus a -16, for a total of -25 kVAR. Then what I want to do from that is determine my net reactive power. Net reactive Q is equal to positive 20 plus -25, which gives me a net minus 5 kVAR, which means predominantly it is capacitive since it's a negative. Then what I can do is I can make a determination of the apparent power of the system, S P squared plus Q squared, square root of that, 24 squared plus minus 5 squared. And that is going to give us 24.5 kVA for apparent power. Well, so what so far? Well, this is good stuff. Think about what I can do now. If I wanted to know what the total current in this circuit is, I know that S is equal to I times E. Solving for current, I would have 24,500 volt amps divided by my source voltage of 380, and I would have, for the total current in this system, 64.5 amps. Wow, that was really pretty easy when you think about the complexity of that circuit. That is this value right here. That is the total current that source provides. I'm providing circuit protection for that, then I know the value, for instance. Then if I wanted to know what the power factor of the system was, the power factor of the system is going to be the active power over the reactive power. So the active power we said was, I forgot, 24. And the apparent power, did I say reactive again? I'm sorry. It's active over apparent, P over S. And this is 24.5. So it's going to be close to 1. And indeed, we found out it is 0.979. Now, when we talk about power factor, we always use a descriptor of leading or lagging. Since this is negative, it makes it primarily capacitive, and current is always the thing that the descriptor is based on. So current is leading voltage in a capacitive circuit. So we would say that it's 97.9% power factor, and it's leading. Okay, I just think that's just the neatest thing and the greatest application of this knowledge that we've acquired here. And all of these things are very measurable with meters, and we could do this and solve a very complex problem relatively simply.